So the 5 circuit patterns we've done so far this week. We've got Ohm's law, and that means across any row. So for any element, we know that the element's current has to be proportional to its voltage and inversely proportional to its resistance, so that we can solve V equals IR across any of the rows. We know Kirchhoff's loop rule. One is the voltage rule. So sometimes you'll hear Kirchhoff voltage rule or Kirchhoff loop rule. And that's saying the voltage that's put in from the power supply has to get used up by all the resistors it meets along any closed loop or closed path. Another one is Kirchhoff's junction or current rule. The current rule says that the current going into a junction is equal to the sum of the current leaving the junction. This is a conservation of charge statement. It's saying that the charge that goes into a junction has to split up over the branches and equal the charge that leaves the junction. Now, I organized them in this way, even though it's not the order it was presented in class. I organized it in this way because these three, Ohm's law, loop law, and junction rule, are statements that are always true. They're true for every type of circuit. So for Ohm's law, this is true for every element in a circuit. So every battery, every resistor, every light bulb, every element obeys Ohm's law. The whole circuit has to obey loop rule. And that has to be true because this is saying a conservation of energy. So it's always true. The energy put out by the battery is used by the resistors in its path. Finally, junction rule is another one of those always true rules because this is another rewording of conservation of charge. So if we take our 3 rules that are always true, and then we have the 2 rules that are specific, the series rule, whereas if you find items in series, they have the same current as each other. In parallel, they have the same voltage as each other. Those 5 together are our 5 circuit patterns. So let's do those in a little bit more detail so you see one example of each rule, then we'll put it together as like, how do we tackle this big circuit thing going on here? So how Ohm's law gets applied in a larger circuit is that across every row, voltage is equal to current times resistance. So for instance, in this circuit Sudoku, in this particular pattern, I see automatically that the current in R1 is 6 because the voltage is equal to the product of current times resistance. And similarly, the current in R3 is 4, or sorry, is 6. So circuit pattern number 2 then. This is the one where if you can identify items in series, you know that they have the same current as each other. In this case, let's say we know that the current through R1 is 0.17 amps. The other currents we automatically know then, well, we automatically know that R1, R4, and the battery all have the same current. Because imagine that 0.17 amps goes through R1. When it splits up and it reaches the junction, the red and blue currents must be less than 0.17. But whatever they recombine together to make the total current flow back through R4 and the battery. This buys us the information that I4, the current over the 4th resistor, is 0.17, and so is the supply. The loop rule. This is the conservation of energy one. So let's say we have 2 9-volt batteries. That makes 18 volts total. And we want to find a loop. Along the outside loop, I see that 18 volts is used by R1 and R3. So it must be that 18 volts is 18 plus something equals 6. So the missing voltage using loop rule, R1 must have used 12 volts. So let's just check. Along this loop, 18 goes in, 12 volts gets used, 6 volts get used. Perfect. All the energy has to get used up. Rule 4 is the parallel rule, and we're going to stick with the same picture. For the parallel rule, let's say that I knew the 12 volts, right? I knew that from before. Now let's find the voltage drop over R2. The voltage drop tells you how much energy is used by the second resistor. So for here, R2 and R3 are in parallel. And if you're looking at this and you're like, Miss Pasega, that's not in parallel. Yes, they are. They're in parallel because they share junctions. This top junction is electrically connected to 2 and 3. The bottom junction is connected to 2 and 3. So these two are in parallel with each other. They're electrically parallel, just not literally parallel. That means if we know that the voltage drop over R3 is 6, we automatically also know that the voltage drop over R2 is also 6. I do have a word of warning for this one though, because sometimes when people look at this in the circuit Sudoku, they look at it and they're like, oh, that means 6 plus 12 plus 6 is 24. Yeah, but we don't double count things in parallel. Since an electron can only go over one path at a time, let's say I chose this outer path. Over this path, 12 plus 6 is 18. Over the inner path, 12 plus 6 is also 18. So just keep in mind that you don't double count things in parallel. So what I do to help remind myself not to double count is sometimes I put a little box around things in parallel and be like, these two are in parallel with each other. So I only count their voltage once. So 12 plus 6 is 18, not 12 plus 6 plus 6. Which brings us to the last pattern, the perennial favorite, Kirchhoff's junction rule. And this should say that this is the 5th pattern. The last pattern by Kirchhoff's junction rule. This means that all the electricity that flows into junction A splits up. If 5.5 amps goes into junction A and an unknown amount goes down and 2 amps goes to the right, that means I have my current going through I1 would be 5 equals something plus, 5.5 equals something plus 2. So I1 must equal 3.5 amps, right? Ooh, and when it gets back together, let's say the current goes through I1 and I2. When it gets back together, it recombines. This 3.5 amps plus the 2 amps that goes through the outer path, those must recombine to make 5.5 amps again. Right? So if I've done this right, I should have a self-consistent problem. 5.5 amps goes in at A and comes out at B. So what happens when you put all of these in a circuit is you're going to go from rule to rule to rule and see which ones you can apply. All the problems should be self-consistent, which means it doesn't matter which order you do them. So, off the top of your head, is there an easy one we can knock out of the way right to start?
Would the first one be 15?
Yeah, and how'd you get that one?
Because 2 times 15 equals 30.
Perfect. So Ohm's law, you're generally not going to see me show my work for it just because it gets done across each individual row. So 15 is 15 times 2 is 30. Now, since it doesn't really matter where we start, but I look at it and I'm like, well, those are in series. I can do those really quickly. And I color code. So let's do this. R1 and R2, they're in series with each other. I'm going to label their current as 2 amps. R3 and R4 are in series with each other. Notice that when I draw this current going through them, that there's no junctions to split it up. So both 3 and 4 are in series with each other. This finds us currents. I know R1 and R2 both have 2 amps of current flow. And I know they're both 2 because let's say 2 electrons go through R1, those same 2 electrons go through R2. Similarly, these must both have 3 amps, and that buys us more information. We can solve Ohm's law across this way. Now what? All right, I'm going to cycle through rules that I've used and can apply. I applied series rule. I applied Ohm's law where I could. Let's try junction rule. At this junction, 2 amps flows in, 3 amps flows in. So they must recombine so that 5 amps leaves that junction and goes through the battery. So I found the total current using junction rule. And notice that that works at either junction. This junction on top has 5 amps flow in, split up into 2 and 3. On the bottom, this has 2 and 3 flow in and go recombine to make 5. Okay? So now we're stuck. You reach this point. We've applied Ohm's law as much as we could. We applied series already. We don't have anything in parallel, so I can't do that. And we did junction rule. The only one we haven't done is the loop rule. So let's follow this instruction. So along any closed loop that starts and ends at the battery, the voltage from the battery must equal the voltage used by the resistors in that loop. So I'm going to define a loop that starts and ends at the battery. On the inside loop. On the inside loop, the voltage from the battery. So I'm going to write that as dV supply. The supply gets used up by R1 and gets used up by R2. Since I defined this as the inner loop, I do not care what happens in the outer loop. For the inside loop, that means 50 volts goes in, 50 joules per coulomb goes into the circuit. R1 uses up 30 of those joules per coulomb. So that dV2, delta V2, has to be equal to 20. It has to use the remainder, the difference. It has to use the amount of energy that's left over. And solving across that row with Ohm's law gives me 10. All right, so we did the inside loop. What about the outside loop? In the outside loop, I still need to use the energy put out by the supply. The supply puts out 50 volts, and those two resistors, 3 and 4, have to use them up. 3 uses up 15 of them. So that means that 4, the fourth resistor, must use up 35. Now, the reason I wanted to give you a funky number here is because sometimes there's nice whole numbers and it comes out really beautifully and you're like, yay, I feel good. But it's not always like that. So this 35 divided by 3 is 11.67. If you get a decimal, it doesn't mean you did it wrong. So don't be worried if that comes up. Okay, so let's see some hints that I've used here. Hints were that I cycle through If I ever get stuck, I just cycle through my rules and see what have I used, what have I taken to the farthest point that I can, and see where I'm vulnerable, where I haven't really used yet. I label loops if I can, and I use color coding to label my currents. That helps. Let's show you a harder problem. Let's show you a harder problem and more tips and tricks. So in this problem, let's start off, and since it doesn't really matter, let's start off with identifying things in parallel. R1 and R2 are in parallel. So I'm going to draw a little box around their voltages. These must have the same voltage drop as each other. So if R1 uses 6 volts, R2 uses 6 volts. R3 and R4 are in parallel, so I'm going to throw a little box around that. R3 uses 12 volts, so R4 uses 12 volts. And that helps because when I am, oh, don't do that. Sorry, let me try and get the thing to focus. Come on, camera. You can do it. Nothing? That's so out of focus. All right. There we go. Okay, so the reason we put the little boxes around things in parallel is to remind you to not double count. So this isn't 6 plus 6 plus 12 plus 12. This is 6 ones plus 12 ones equals 18. Right? And that's because the electrons can only take one path at a time. So if you imagine that I defined my loop as the supply, R1 and R4, then I would have 18 from the supply is used up by 6 for R1 and 12 for R4. I wouldn't double count those. Okay, Ohm's law everything, so that makes this a 3, a 1.5, a 3 again, a 1.5 again. Using Ohm's law across the row, because 3 times 2 is 6, and all that follows. And then that leaves one last trick I can use. I've used Ohm's law. I've used the parallel rule. We don't have anything in series. We've used loop law to get the total voltage. I need to use junction law. That's all that's left. So if 3 amps goes through R1 and 1.5 amps goes through R2, that leaves the total current running through this circuit. And let's watch this junction. The total current would be 4.5 amps flows out of this junction. That must be the total current of the circuit. 4.5 amps would go into the battery and into this junction again. So my total current is 4.5. Across the last row then to get the equivalent resistance. And until next week, the only way we're going to be able to calculate equivalent resistance is to divide across this row. 4.5 times 4 is equal to 18. Next week, I'll show you a different way to calculate equivalent resistance. So the new hint or trick that I gave you here was to put little boxes around parallel parts of the circuit to identify their voltages as being the same. Right? All right, last one. Let us use that tip. There we go. So let's use that tip. We have 2 sections that are clearly in parallel. So those must have the same voltage as each other. That allows me to quickly identify the voltage drop over R2 is 6, but I can't do R5 and R4 yet. I'm going to leave that box there, but we can't tackle it yet. So we can't deal with voltage. Let's deal with current. I see that the current from R1 and R2, there's 3 amps that goes through R1 and 2 amps that goes through R2. So that at this junction, 5 amps must come out. 3 amps and 2 amps goes in, so 5 amps must flow through R3. That same 5 amps has nowhere to go. It is trapped in this path. So that same 5 amps flows into R4 and R5. There, it splits up. One of the amps goes up through R4. That means it must have put 4 amps going down through R5. At the next junction, they all recombine. So what I want you to imagine is their current is just recombining and combining as it goes through. 5 amps then flows through R6. 5 amps then flows through the battery. And now that I've labeled it, I can read all the currents out quickly. So use color coding to help do your currents. 5 amps leaves the battery, splits into 2 and 3. 5 amps goes through R3 and then hits this junction. 5 amps splits into 1 and 4. Recombines so that 5 amps goes through R6. And that same 5 amps, all that current, imagine this is like water, right? All 5 gallons of water goes back through the battery. So don't add them up, it just equals 5. You don't double count things. This gets us almost enough information, so let's Ohm's law some things. 4 divided by 5, 0.8. 30 divided by 5 is 6. 5 times 3 is 15. All right, so now we're looking for a voltage. We've used the parallel rule. We've dealt with junction rule. We've identified things in series. We can't use Ohm's law anymore, so it has to be loop rule. So let's say I define a loop, and I say my loop is going to be electrons go through the supply. Then they go through R1. They go through R3. They go through R4. And finally R6 before they head back to the supply. So I'm defining my loop as going from the supply through R1, R3, R4, R6, and back. And along that loop, the supply's energy has to get used up by all the resistors in its path. The other resistors, like resistor 2 and resistor 5, I don't care about because they're not part of my loop. Think of it as a path an electron could take. It could go over path 1, 3, 4, 6, but it can't go over both paths 1 and 2 simultaneously. So if an electron was given 30 joules of energy to start, 6 of them is used up in the first resistor it meets. 15 is used up in the second resistor it meets. I don't know the voltage of 4, but R6 uses up 4 more. That must mean that there was 30 volts in, 25 volts used, so 5 volts must be left over. The voltage used up by the fourth resistor must be 5 volts. And since it's in parallel, R5 must also be 5 volts. It's not like the 5 volts get split between the two paths. each of them has 5 volts, which means I have solved this circuit. So to recap tips and tricks, use color coding to show that the current from the battery splits up and takes different paths, but always recombines at the end to make the total current. If you label your currents as you go, that makes it easier to keep track of. I would also circle all the parallel sections of the circuit to really quickly identify, not to double count these voltages. Um, and then finally, when you go through and you're stuck, there's always a way forward and it doesn't matter which way you take. So do a checklist to yourself. Be like, okay, well, we have already tried. We're done with Ohm's law. We can't do more with it. We don't have anything in series, right? Check off which ones you could still use. Because even if you're stuck, there's always a way forward.